moving on to our major milestones. So on September 6th, we had our first meeting with Brian Utter, our sponsor. This was basically to go over what he wants for those floor plans, what we need to put in the building. Then on November 15th, we met with Jacob Carlisle, who's the architect that we work with. He talked to us about what we needed to change on our floor plans due to code, and we just had to change things, add an elevator and things like that. Then on November 20th, we completed our initial 3D Revit models and plans. Then January 22nd, we got our final floor plan approved by Brian. So this was just like where we were putting things. Then we worked really hard on like getting the rest of the code done. Then on February 27th, we started our structural, mechanical, plumbing, and electrical. And now we are working on finishing our final construction documents. So for our team's responsibilities, Fox was architectural, Emily worked on structural, Anthony worked on mechanical, Lucas worked on electrical, and I worked on plumbing and fire protection.
So our first functional requirement was redesigning the current site, and this is our final result of the current site. We had a few requirements from Scheineban. One of them was that a charger bus should be able to access the property, so we had to redesign certain parking spots. And we also maintained the same amount of parking spots. Also, one of the complaints from Scheineban was that people use the current site to use it as like a quick turnaround, to make a quick U-turn. We prevented that from happening in our new design. We also added some vegetation and seating into the design for a welcoming feeling. And over here, we added ADA compliant parking spots. So this is the concept of the building. We started off with the current building, like Lucas showed you guys before, the old Hardy's restaurant. The first thing we did, we added a simple volume to the building, about 26 feet high. And then we looked at how the sun orientates around the building. We looked at both the summer path of the sun as well as the winter path of the sun. The next thing we did is we divided the volume up in two functions. One of them is an office function, and the other one is kind of a public mixed-use function. Next, we added a roof opening for natural daylight to flow into the building, creating a beautiful atmosphere inside of the building. The next thing we did is we redesigned the current roof to let the current building blend in with the additional building. And then next, we added some vegetation in front of the building to create a welcome and engaging experience. So this is the final design of Scheineban. The redesign of Scheineban features a modern symmetric aesthetic harmonizing with the surrounding architecture. In this building, we decided to use two different materials, and both of them have their own function, creating two kind of separate worlds from the outside. First off, we have the light gray brick that represent the mixed-use public space, accessible to everyone. And in contrast, we have these wood black panels that are designated for office spaces. And in this render, you can also see how the community will be using the green area in front of the building. After our first meeting with Scheineban, we got our first design alternative. This was our very first floor plan. And right here we have our final floor plan. A lot of difference. This is actually an architectural construction sheet. So let's zoom in to this floor plan, and we start off here. When you first enter the building, you see the break room that can be transformed into a concession stand when needed. And then we also have this seating area right here. As we move on, we have the green room that contains two showers where artists can fresh up before they perform on stage. Over here we have a utility room, and right next to it is an elevator that we had to add due to code, and on the left of it is a mechanical room for the elevator. So over here we have two bathrooms, one man and one woman bathroom. Both have two ADA compliant stalls, and we have everything according to the codes. Then over here is the big multi-purpose room that is 2,650 square foot big. This area will mainly be used for performances, events, or could potentially be rented out. Over here we have a storage space where Scheineban can store all their tables and chairs. Then over here is another storage room that can be used as kind of a classroom, such as engineering room, which was one of the requirements from Scheineban. Then over here we have more storage spaces. The one on the left, the bigger one, is from Scheineban, and another requirement from admissions was to have a storage space inside of this building as well. where they can store their golf cart. And due to code, we had to add a sprinkler room over there. So after our first meeting with China Van, we also designed a second floor plan, which mainly consists of office spaces. And this is our final construction sheet for the second floor. Like I said before, the main function is just office spaces. So we have 7 offices inside of this building that vary between 11 and 12 feet to 11 by 18 feet. Then we also have 3 conference rooms right here, and the one on top here can be potentially transformed into a podcast studio. Then over here we have 2 unisex bathrooms that are both ADA compliant, and we also decided to add a little coffee counter room. Then over here is an open office space. This space could potentially be rented out to different companies. We wanted to keep this open office space as minimalistic as possible and give them as much space as possible so they can arrange it however they would like. These are the final construction sections. Let's zoom in on this one. In this view, you can clearly see how tall the building is. The roof height is 26 feet high, and the ceiling height inside of the multi-purpose room is 23 feet high, so it's quite tall. And right here we have an architectural render of how people will be using this space. So right here, this is straight out of Revit, our building, and as we explode it, you can see how the rooms are orientated inside of the building. So this is the main lobby in China Van. We wanted to go with a modern aesthetic using minimalistic materials like the white plaster, wood, and black tints. We added a green inner garden inside of the building that also serves as a seating area because we wanted to bring nature inside of the building. Here you can see how the community is using this spot. And then right on top of it is a skylight where, it's a skylight where natural daylight can flow in right to the building on top of the inner garden. So right here is the second floor. Same design, minimalistic, same materials. We added this glass railing so people can look down onto the first floor, and we decided to expose the structure here, giving a really cool effect. So this is the open office space I talked about earlier. This is our initial design, but China Van can design it however they would like. We gave them a lot of space, including a storage area right there. And then over here you can see the elevator. Fun thing to see is we added these light strips right next to the ceiling because we offsetted the ceiling from the wall, and this is consistent throughout the whole building, creating a beautiful effect. So this is the big room, the big multi-purpose room that will be used for events, gatherings, and can potentially be rented out to, for example, a church. We decided to go with black materials because that is good for video production, and we added patterns into the wall, and by adding lights to it, it basically creates arrows pointing down towards the stage, so the user will automatically kind of look towards the stage, creating a really cool experience. So this is the back of the building. These 2 doors are storage doors for China Van, and the one right next to it is for admissions. And then over here we have a bunch of mechanical equipment that's already there.
Alright, next we will be transitioning into the engineering design and analysis section of the project, starting with the structural concentration. And the design load for that was as follows. So the dead, live, and other loads were determined using ASCE 7, as well as the LRFD and ASD load combinations. And then beams, bar joists, and column layout was created based on the floor plan that we created, just what was necessary in all of the locations so that the building wouldn't end up fall over. Then the bar joists were sized based on the spans of that floor plan and the loading capacity of bar joists that are pre-sized and already exist. And then the beams for the building were designed based on the AISC's steel construction manual. And then the foundations were sized based on the joist beams and columns of both the second floor and the roof structures. And then next what we're going to be doing is zooming in on this area up here to do an example load trace through one of the more complicated beam support systems in the building. So zooming in there. So we start off with this external beam. It is simply supported, and that means it'll have two reactions on the end where it is being supported. But the thing is about this beam, it is being supported by two cantilevering beams. So those reactions will then become point loads on the ends of those beams that are supporting it. And then the reactions that are occurring on these beams will then become point loads on the cantilevering beams that are supporting it. And these beams are then supported by columns, so then those will go directly into the columns and down to the foundation. Next we will be looking at this final beam in that load trace for an example beam calculation. So here we have a free body diagram of that beam. We have the uniform load on the top from the tributary area of the roof. And then light gray are those point loads from those beams that it is supporting. And then the dark gray is the columns, so those reactions. And then from that free body diagram, we get our shear diagram. And then if you go from left to right, it aligns with the beam. You can see how the interior shear changes as you travel through the beam. And then from our shear diagram, we then get our moment diagram. So from this moment diagram, we see that we have an unbraced length of 7 feet. That's where that length there dips below that x-axis where it's negative. And then we also get a required moment of 82 kip feet. Now, according to the AISC Steel Construction Manual, a W18 by 35 is sufficient for that negative moment and for that positive moment. But then if we move on to deflection, according to the IBC, a typical roof structure is a maximum deflection of the length of the beam over 240. And then for this particular beam, 40 feet, we get a maximum deflection of 1 inch. And then according to the Steel Construction Manual, a W18 by 40 beam with a moment of inertia I value of 612 inches to the fourth yields a deflection of 0.74 inches. So based on this analysis, we choose a W18 by 40 beam for just this one particular.
Alright, so with the mechanical part, first thing we did after the floor plan was finalized and checked by Brian and the architect was we ran a load count. This load count was run by Carrier Software Hourly Analysis Program, which was first provided to us by RTM. This load count incorporated the 2018 IMC, as that is the code that the city of Urban Bay uses. Little things about the load count, but the main things of it, pretty much we have to include the weather conditions for this area. Also include the U and R values of different materials that are going to be surrounding the building. So walls, windows, floors, and knowing the U and R values of those. Also knowing the orientation of the sun, as Blas previously mentioned. And knowing the occupancy load that will be throughout these specific floors. Once that was all completed, this gave us our heating and cooling loads for the entire building. So the building is zoned into 3 different parts. Floor 1 is zone 1, floor 2 is zone 2, and the multi-purpose room has its own zone as zone 3. And as you can see here on these isometric views, you can see a ton of colors. These are actually the ductwork that is going to be supplying all the air, all the return, and all the exhaust for the bathroom. And you're going to see the blue supply, pink is return, and green is exhaust. So starting off with the first floor, we decided to go with a constant air volume system. This is due to, meaning that it's going to be one set temperature and one set thermostat for this floor. This is due to, like Blas mentioned, this floor being mainly just like a lobby area and not having that much of a diverse load and not having much occupancy. From the load count, we got around a 7.5 ton load for this floor, so we sized our RTUs for that, and that's the model number. We decided to go with Grand York. All this ductwork was sized by the load calculation CFM and using ventilation rates from the 2018 IMC. And we sized all of our ductwork using the McQuay duct sizer program, which is provided to us by RTM. So for the second floor, there's a lot of different color here, but starting off with the second floor, we decided to use a VVT system, which stands for Variable Volume and Temperature System. It essentially utilizes dampers within the ductwork to allow the user to be able to regulate airflow throughout different zones. So a thing that our client did mention was that he wanted to have more temperature control for this new building. So we have some offices here, you can see little boxes in between the HVAC work. These control the different temperatures for different zones throughout the building. This second floor did give us a bit of higher load as it was 12.5 ton load. This is due to the higher occupancy due to the offices, conference rooms, and having large windows. For the multi-purpose room, we got around a 15 ton load, and the driving force for this was the high occupancy that Brian would like to have in this room, of having around 100 people in there. And for the roof plan, there's not much here except just the RTU placements and the exhaust fans, which you can see in green. Just an example of a code that we exactly had to follow is that any mechanical exhaust fan that is on a rooftop needs to be around 10 feet away from any air intake. So I know you might see that these are a little too close, but we did get it flagged and checked by the BE I was working with, and it's around 11 feet.
So now we're gonna move into the electrical side of the building. So first, I'm gonna talk through this one-line riser diagram, which shows how power is distributed throughout the building. Then I'm gonna go through the feeder size calculation, show some engineering analysis, and finally I'm gonna end with some receptacle layout, how the code kind of affected that. So first, over here, we have our utility transformer, so it's 12,470 volt coming into 120,208 volt, and that runs to our main distribution panel, which is a 120,208 volt three-phase 4-wire panel. It has an SCCR rating of 25 kiloamps. And then from the main distribution panel, we distribute power to 6 panels that kind of power the whole building. So P1 and P2 kind of handle the bulk of the load, so that's like the general receptacles, the lighting, kind of the bulk of the load of the building. Then we have a dedicated AV panel because the equipment is pretty noise sensitive, and so everything on there will have isolated grounds to help prevent that. Then we come over here to TX1, which is a step-down transformer, and that's 30 kVA, 208 volt. We have to drop that down to 120, 240 single phase, and the reason is on LP1, the faculty, or Brian, he requested 2 Torbus plugins for when a Torbus comes and also the golf cart, but they are 240 volt, 50 amp split phase. So we have to drop that to 120, 240 single phase to be able to power those properly. We also have a 200 amp automatic transfer switch that's also backed by a 60 kVA backup generator that powers our CLD panel, which is where the critical loads will all be. And then our final one would be the HVAC panel, which will be on the roof, so it's NEMA 3R, so it will protect everything from rain, sleet, or snow, and that powers the 3 rooftop units like Angie. Now here is a feeder sizing example. So the one we're going to go through is the main distribution panel to the step-down transformer TX1. So the first thing you do is calculate the transformer primary current. And so that's the top equation, which is the current equals the KVA times 1,000 and just get it to VA. And you divide that by the square root of 3 times the line-to-line voltage, which in this case is 208. And you do that and you get 83.3 amps. But then according to NEC 215.2, which is the National Electric Code, if it is a continuous load, so it means it can be running for most likely longer than 3 hours continuously, you need to times that by 125%. So we take that number times by 1.25, get 104.1 amps. Then we come over to NEC table 310.16, and we're gonna do 75C as that is what the panel terminals are rated for. We're gonna come down, you see number 3 is only 100 amps, so that's not good enough. 150 or 2 would be for 115 amps, that'd be big enough. But just for added safety, we're gonna go down to wire gauge size 1, 130. And so there you see your final selection is single gauge wire, copper wire, THHN insulation for 130 amps at 75C. And so now we're gonna go to some receptacle layout. And here we have the storage area receptacle layout. So here, the TVP-LCI-WP, that stands for Torbus plugs, ground fault circuit interrupter, weather protected. So weather protected just has a cover on it. And the ground fault circuit interrupter, because this is kind of a storage area, inside and outside, you're gonna kind of be moving, you wanna prevent people from electrical shock. So all the outlets in this area have that. And so you see both of those with their home run to LP1. Then here you just see some general receptacles, which are 120 volt duplex receptacles, and their home run is in panel 1 because it's on the first floor. And they are spaced, it's 6 feet between every receptacle, so 12 feet between 2, 6 feet of every doorway, and all that comes from the National Electric Code. So it's in compliance with NEC 210.52, 210.8, 406, et cetera, et cetera, et cetera.
Okay, and now moving on to the plumbing. This is an isometric of our hot and cold water. As you can see here, the red will be your domestic recirculation. So down here on the bottom is our first floor. This will have 2 showers, a sink in the janitor's closet, and then it will have a men's and a women's restroom. Then on the second floor, you will have 2 smaller bathrooms. Now moving on to the plumbing plans, this will be your first floor, and this will be your second floor. All of this plumbing is in compliance with the Illinois Plumbing Code. Hot and cold water will have shut-off valves, so this is just in case something were to happen and you have to turn off one of the toilets or one of the other fixtures. We will have a recirculation pump for hot water, and this will be in our mechanical room. This is so we keep hot water in our building at all times. And then we will be using a DuraPower 55-gallon electric water heater. This is just based off our change in temperature, how many fixtures we have, and other things. Now moving on to our sanitary ventilation isometric. So the dotted black line is your ventilation and your green is your sanitary. Same thing as the plumbing, we have the 2 showers, the sink, the 2 bathrooms, and then the 2 bathrooms upstairs. So here is our first floor and this is our second floor. All sanitary and ventilation is just like plumbing where it follows the Illinois Plumbing Code. All fixtures will have sanitary and ventilation, and you can see how those are connected through these pictures. We will have the ventilation go up through the roof past the snow line. This is so nothing gets in that pipe. And then we will have 2 floor drains on the first floor bathroom. This is just due to it being a bigger bathroom. We want to have those 2 floor drains. And then on the second floor, we will have 1 floor drain in each bathroom, as you can see here. And then we have waste side cleanout, just for if like any plumber has to get in those, they can get in them. And then we have floor cleanup whenever you change in direction. So you can see one here and one here. Now moving on to our sprinkler placements. So this building will be sprinkled, and this is just an example using the multi-purpose room. So I use the National Fire Protection Code, NFPA 13, to get these placements. So I will use concealed sprinkler system. So this means the sprinklers won't be visible. It will be like a little cap. And I use hazard classification ordinary hazard 2. I just did this because of the size of the room, and just because there's going to be a lot of mechanical equipment in this room, we just want to make sure everyone's staying safe. So that means that the maximum sprinkler coverage will be 12 feet or 130 square feet. So as you can see from this spacing, that each of these fixtures will only have that 130 square feet. So that's how I space them. And this will be a wet pipe system. So that means when a fire would happen, the sprinklers would go off right away instead of waiting for that water to come in. Then we have weekly obstruction testing, just making sure that nothing is in the way of those pipes. And alarm devices will be checked monthly.
So now we're gonna move into some broader impact for this project. And so number 1, it will expand Shine FM's outreach and influence. And so this will help them build stronger connections with local and regional audiences through the podcast studio, through various events that they could hold in the multi-purpose room, or other things, and also for the extra office spaces, more people will be able to work there. We'll also strengthen community engagements. This will foster new partnerships and collaborations to enhance impact through the larger team and more people. And those both kind of flow into this final one, which amplify the gospel message. So utilize Shine FM as a platform to reach and share the good news of Jesus and all that they do. And this is kind of the main purpose of Shine FM, is to share the gospel, transform people to be like Christ. And so something we were challenged about is kind of what's the monetary value that comes from this project? Because when we think engineering, you kind of got to think money in some sense, because obviously it will help Shine FM, and it's kind of harder to work around, because when you hear and receive the gospel, you don't just get $100 in your bank account. I mean, you get a lot more in eternal life, but it's not that easy. But some statistics kind of show how this can have an effect. Is so couples who have religious affiliation versus couples who do not are 15% less likely to get divorced. Then when you move past that, children grow up in a 2-parent household versus a 1-parent household are more than twice as likely to graduate from a 4-year degree. And then moving one more step, people who graduate from a 4-year degree and go on to work versus people who do not graduate with a 4-year degree and go on to work. The people with a 4-year degree earn on average 180% more than the other people. So there is some monetary value in this project. And finally, just kind of future plans as we wrap up. So number one would be to finish the construction documents. At the beginning of the semester, Professor Reagan challenged us to get 50% of the construction documents. I think we're actually gonna get to 75%. So we're pretty happy with the progress we've made. Number two would be to enter the NCES Engineering Education Competition, which is a competition that the NCES submits that we gotta make a new poster, a 7-page document, and a 1-page abstract to submit to that. Number three would be for Shine FM to fundraise for this new addition, to be able to break ground. And then number four, they would pass off the plans to the local engineering firm, would check all of our work, would finish it up, and then they would be able to move forward. Any questions?